All right, so a lot of times when you're asked to calculate the volume of a solid, it's described, at least in Calculus 1, as a solid of revolution. So what that is about, something like here. So typically you're told, well, for example, this area bounded by y equals x and y equals x squared about the x-axis. So let me start us out here. Um, so y equals x is like this, y equals x squared is like this, basically. Something like that. I happen to know the points of intersection are the origin and 1, 1, right? If you set x equals to x squared, what happens? You get x squared minus x, which is x times x minus 1, equals to 0. So therefore your points of intersection are x equals to 0 and x equals to 1. All right. So that's the area we're thinking about. And then we're revolving it around the x-axis. So like that. So what I usually draw is like a dotted version of the same thing, trying to do the same thing. Well, you know, man, spirit is willing, the pen is weak. So here's the revolved, the revolved one around the x-axis like that. And so if I was so foolish as to try to draw a picture of it, I won't. I guess I will. It's something, crudely speaking, like this, you know. It's like a cone on the outside with some kind of weird, curvy, non-circular, non-right cone cut out of the middle of it. Anyway, so the volume of this, what you can do to calculate it is to imagine chopping this weird thing up into discs, all right, or washers really. So there's one, and then like that from the inside, and then it's got some thickness, you know. And so like over here, all I would draw would be this. So there's part of the washer, there's the other part of the washer, and then you have to imagine it like a pineapple ring coming out of the page and then into the page like that. This is just the intersection. I can't draw with anything like that piece and that piece. All right, so if I can calculate the volume of this particular washer, then I just have to add, you know, the volume of them up as it goes from x equal to 0 to x equal to 1. Notice that the thickness of the washer is clearly the x. And so what I do is I try to figure out what's the inner radius and what's the outer radius for the washer. So, you know, this would be R in, and this here would be R out. R in is pretty clearly, well, I mean, it's y. Which y? It's the x squared one, right? So R in is x squared. And so just as a rule of thumb, if your thickness is dx, that means you want formulas for the inner and outer radius in terms of x, because you're going to do an integral. I mean, if you write down dx, that means you're going to do an integral in x before you know it. R out, on the other hand, is x, right? And so I'm gonna, I guess I'll draw it over here again. So basically, we're looking at this. Oh, I don't know why I drew it that. Oh well, anyway. I'm trying anyway. So what's the volume of this thing? Well, dV is the area, right? And now the area of this is the area of the inner circle, which is pi r in squared, right? Subtracted from the area of the outer circle, which is pi r out squared. So you have pi r out squared minus pi r in squared. I'll just factor out the pi, right? That's the area of that washer, and then times dx. Of course, for this one, this is just pi x squared, right, minus x to the fourth, because x squared is x to the fourth dx. And that's for 0 less than or equal to x less than or equal to 1. So the volume, integrate pi x squared minus x to the fourth dx from 0 to 1. And there you have it, pi 1/3 minus 1/5. I love integrals from 0 to 1 of polynomials. In other words, 5 minus 3 over 15, 2/15ths, so 2 pi over 15th. There you have it. That's the volume of this rather strange shape. Okay, so let's take the same area and, bonus example, all right? So example 3 tilde, rotate around, why am I making my n into an h? Rotate around y-axis, all right? All right, so here's the picture in that case. So this time it rotates over to here, right? And my little washer horizontal this time, right? And so like dv, the thickness is dy, right? So I want to write the inner radius and the outer radius in terms of y. This time the tables are turned. Our in is given by the line, right? So anyway, so pi r out squared minus r in squared dy. So that's pi times, let's see here, the outer radius. What is x? So this r out is equal to the right x, right? Which is, by the way, the square root of y. I mean, if y is equal to x squared, then x is equal to the square root of y, since we're in the positive region over here. Then, let's see here. So what we got is we got the square root of y squared. Well, that was kind of redundant. Minus y squared, because x equals to y is the other one, right? Now, it's funny. This is also from 0 less than or equal to y. Less than or equal to 1. That's just a coincidence here. But anyway, so the volume, integral from 0 to 1 of pi times y, because square root of y squared is just y, so y minus y squared dy. So that's pi times 1/2 minus 1/3. Check it out. So you got pi over 6. So there you go, 2 examples for the cost of 1. So if we rotate around, if we rotate around the y-axis instead of the x-axis, it's different, right? So the shape is different and the setup is different. Let's do another example here. Example 4. Let's see here. How about let's rotate region bounded by x squared plus y squared equals to r squared, and y, let's say greater than or equal to 0. I'm just going to choose the upper half around x-axis. Find volume. Or if the integral is too hard, we'll just leave it at an integral we can't do. All right. So let's see here. What are we facing? This, of course, is a circle, right? It was supposed to be a half circle. And y is greater than or equal to 0, right? Now we rotate around the x-axis like that. So that's this guy, right? Now you got choices. I guess at the moment we've only talked about washers or basically the cross-sectional method. So I guess I'll stick with that for now. So basically we can look at a disk. Let's see here, how do I want to do this? I guess I'll do it like this, like so. Right? So I guess it's fairly clear the radius is this. I mean, radius is equal to y. So dv is pi y squared, and the thickness is dx, right? But let's see here, we also know that y squared is equal to r squared minus x squared. So this I can simplify to dv is equal to pi times r squared minus x squared dx. And that's good for what? For minus r less than or equal to x less than or equal to r. Because these points right here are x equals to r and x equals to minus r, right? So you can imagine putting a disk at each place here, all the way over to here, right? 0 radius, all the way out to radius big R at the middle, and then back down to shrink into 0. Anyway, so the radius squared is exactly r squared minus x squared. And then we integrate. So the volume is equal to the, let's see here, pi. I'm going to pull the pi out, all right? Integral from minus r to r squared minus x squared dx. I'm going to use symmetry because this is an even function. I can do the double the integral trick, integral from 0 to r, right? R squared minus x squared dx. So that's 2 pi. R squared x minus 1/3 x cubed. I have to evaluate that from 0 to r. What does that give me? 2 pi r cubed, right, minus r cubed over 3. 0 evaluates to 0. This is 1 minus 1/3, which is 2/3, so there you have it. 4/3 pi r cubed. This, of course, is the volume of a sphere of radius r. And there you have it. That's how to calculate that, by just chopping it up into disks and adding them up. Simple as that. All right, so you can do other fun, exciting things like what happens if you, say, drill a cylindrical hole out of that, you know? That makes it trickier. Maybe that's in your homework this semester, so I don't want to do it right now. So anyway, I'm going to turn my attention next to the method of cylindrical shells. This is a pretty good sample of examples of the disk method. You can also talk about volumes of revolution around other axes other than the coordinate axes, and if that comes up later, I'll do an example for you guys, but I think I'm going to just go over to shells now. So cylindrical shells. It's example 5. Suppose you want to find the volume of solid formed by rotating, let's say y equals to sine x, for y greater than or equal to 0. I mean, I guess I don't really need that if I tell you what I'm about to tell you, which is that pi, rather 2 pi less than or equal to x less than or equal to 3 pi around y-axis. Okay, so let me show you what I'm talking about. So here's our coordinate. My x-axis, here's my y-axis. So I'm saying, you know, sine looks like that, right? And then I'm just this bit of sine, and then rotating it over here like that. That was supposed to be the same distance, so well, I tried. And so you just rotate that thing around the y-axis, and it's going to kind of look like one of them Jello molds or whatever. And so what's the volume of such a thing? Now, if you were to try to chop this up into washers, it would be kind of a drag because the inner and outer radius both are governed by the formula y equals sine x. So that I'd really have to think hard about. So since I'd rather be a little bit lazier, I'm going to chop this thing into what are called cylindrical shells. So if you can imagine here and here, let me draw it slightly. I'm going to draw it slightly smaller, just to give you a sense of what I'm talking about. It's something like this, right? So we can sometimes think people might call these ribbons. So like you can chop it up into these ribbons, like this, right? And so that is going to be at radius r equal to x in this case, right? And so, and then this height, what is the height? Well, the height is just y, but it's sine of x in this context, right? This is y equals sine x. And so here it is, dv is, let's see here, if you took this thing, right, and you just laid it flat as a slab, the length of the slab would be the circumference of that circle, 2 pi x, right? And here's your sine x. So the area of this thing is just 2 pi x sine x, and the thickness of it, well, if you can imagine that, is just dx. So there you go. dv is 2 pi x sine x dx, and I'd have to do that from where? From here all the way out to there. That's 2 pi to 3 pi, according to my setup. Zero, listen to me. 2 pi and so there you have, volume is going to be the integral from 2 pi to 3 pi of 2 pi x sine of x dx. And that's as far as we can go at the moment, because we don't yet have the tools we need to do an integral like this. This isn't one of those integrals that can't be done. This is one of those integrals that we can't do yet. Very different. In fact, it turns out that this is an integral which is easily dispatched by what's known as integration by parts. All right. So anyway, you know, maybe we'll come back to that. Anyway, I needed to talk to you guys a little bit about these methods of calculating volume, because some schools somewhere might leave out this as a topic, and there is a selection of homeworks here and there which come back to this, and you're expected to know it. So I wanted just to try to be kind and give you a few examples to go off of before you are blindsided by it in the homework. Let's see here. There probably should do another example of this shell method. Let me think of another one. See if I can find a good example in here. Give me a second. Come on. Come on. Where'd you go? Here, I'll try this one. It may or may not go well. Let's try to calculate the volume. Let's rotate y equals x cubed and x equals to 0 and y equals to 1. Rotate the area bounded by these things around the y-axis. Alright, and we'll try to decide whether we want to use the method of shells or the method of washers here. They're not mutually exclusive. There are problems which can be done either way. The sine x example we just looked at is pretty much demands a method of shells, or the investigation of some somewhat complicated precalculus, but anyway, here it is. So let's graph this thing. X cubed, like that. X equal to 0, well, that's this. Y equals to 1, that's this, roughly speaking. And then around the y-axis, well, that's not too exciting. see here, like that, right? So basically, when you rotate it, it creates this over here. All right, now let's see here. Tell you what, I'll try to set it up both ways. If we're going to do washers, I'll do shells first, since we've done washers before. So shells, you have to think about something like this. The shell should be like, in some sense, parallel to the axis. So if I'm so foolish as to try to draw it on the paper in some sort of ill thought out three-dimensional perspective on top of this two-dimensional graph, I don't know. It's like that. I regret it. I regret trying to draw this. Anyway, okay, so dv, right? Again, the radius of the shell is x, so 2 pi x, and then the height is this distance here. In this case, the height is going to be 1 minus x cubed, right? So times 1 minus x cubed, and then the thickness is dx. And I need to do that for 0 less than or equal to x less than or equal to 1. That wasn't too bad. So the volume is equal to, I'll pull the 2 pi out. I got 2 pi, integral from 0 to 1. I'm going to distribute x minus x to the 4th dx. I'm starting to like this example. Integral of 2 pi, and that's 1/2 minus 1/5. And so we got ourselves a what? Try to save myself room for the other example. That's 5/10 minus 2/10, 3/10, 3 times 2, 6. So 2 pi, like I said, 5 minus 2, 3/10. And that, of course, that's 1/5, so I get 3 pi over 5. All right. That's the cylindrical shell solution. The washer solution here, I think, wouldn't be too bad either. So I have to think about chopping it up into washers that are like this, right? I mean discs, really. There's no inner radius. Inner radius is 0, so it's a washer. Excuse me, it's a disc. So the dv there, the thickness, of course, would be dy. So dy, and so we got pi x squared dy. But what is x? Well, the x, this x squared is given by the cube, right? Where y is equal to x cubed. So if I solve that, well, I can just take this equation, take the 2/3 power both sides, that get x squared is equal to y to the 2/3, right? Take the 2/3 power of that equation. 2/3 to, x cubed to the 2/3 is just x squared, which is what I want here. So, bam, pi y to the 2/3 dy. And let's see, y ranges from what? From 0 to 1 as well. I'm sorry, guys, I didn't really elaborate to you on where this 1 is coming from. I know that this point of intersection is 1, 1. That's why I did that. The reason I know that is if I put x cubed equal to 1, that gives me the point of intersection, as x is equal to the cube root of 1, which, by the way, is 1. Okay. Now this, on the other hand, is good for 0 less than or equal to y. Well, the contrast of white on white, But there it is. So the volume then, by the method of disks, I integrate from 0 to 1, pi y to the 2/3 dy. So that gives me pi, let's see, 2/3 plus 1 is what? 5/3. So I do 3 over 5 y to the 5/3 evaluated from 0 to 1. As a certain commander of a venerable fictional action team says, I love it when a plan comes together. Let's see here. So there you go. In fact, math is math, and whether you're a Marxist, a Buddhist, a secular Jew, or whatever, you know, the answer is the same because it's part of objective reality. All right. Where are we? I'm sorry, I meant the general revelation of God. Where was I? So I think that's a good slice of examples here. I'm probably gonna leave it at that. And next, because we're just about out of Calculus 1, so what I'm gonna do in the videos which follow this is get into things which are either a review and just a quick run over test 1 through 4 in Calc 1 of a good year, and also I want to give you a couple of short videos on the epsilon delta method as well as the imaginary exponential method, which are very possibly missing from your previous mathematical experience, and that's unfortunate. Anyway, thanks guys.